Welcome everybody. Unfortunately, Ilyas Khan had to fly away to the US last minute for some board meeting of Quantinuum, but he wishes you all very welcome and just have fun. Let's put it like that. Okay, I'm going to start. This is what I'm going to talk about. What is this? From quantum pictures for kids to quantum AI logic. I don't know. I've got way too many slides, so I don't know where I'm going to get. I'm going to do the smart thing. I'm going to time myself. Timer. I mean, I'm not good in phones, but okay. Start. There we go. Okay. Let's move on. The language of quantum. This is John von Neumann. This is what John von Neumann said. Like 5-6 years, a few years after he published the book, Mathematical Foundations of Quantum Mechanics. So quantum formalism is due to von Neumann. He didn't just do game theory, he didn't just do all this mad stuff. He actually also did quantum formalism. And a few years after he actually launched the book, which still is kind of quantum formalism as we know it now, he basically denounced his own brainchild. That was von Neumann, and he said, this Hilbert space stuff is really not something we should be using for quantum. Was never intended to be. Okay, that's Schrödinger. So what did Schrödinger say? Exactly the same year as von Neumann denounced quantum formalism, Hilbert space, Schrödinger said that, like von Neumann, when he started to look for other stuff, he was focusing very much on quantum measurement. He said the structure of quantum measurement is what clearly makes quantum different than classical. At the same time, Schrödinger said something completely different. He said what makes quantum different than classical is basically the tensor product. That's what Schrödinger said. So there was a completely, von Neumann being like the biggest mad genius, maybe except for Grothendieck for the previous century, everybody followed von Neumann, nobody followed Schrödinger. This is a dude from here, Roger Penrose, in the maths department. And basically, at some point, he started to draw these pictures somewhere in the early 70s. He was fed up with this sort of tensor notation, and he said, this is not the way we should write things down, we should use pictures instead. That's what Penrose did. And he was an undergrad. He was an undergrad here at Oxford, I think, at the time. Okay. So what we then started doing quite a few years later was actually trying to realize Schrödinger's view using Penrose's pictures. So Schrödinger's view, to articulate it, is like to rebuild a quantum formalism where the tensor product is the first-class citizen. The first-class citizen. There's no other, so there's no sums. So Dushko and I, we wrote a paper in 2006, quantum measurement without sums, and then we had a whole bunch of papers without sums, because we hate sums. So we want to get, so okay, anyway, that was the program. In 2005, this was a year later after I published my paper with Sampson on categorical semantics of quantum protocols. So that's culture, you know. If this thing I could never have published in any decent conference because it's too simple. It's too simple. People want, you have to show yourself off and show complicated stuff like category theory if you want to be accepted. 13 years later, so we actually have this book. We had this book. Which basically was the realization of the program quantum formalism purely in terms of tensor product. That's what this book is. This has been the course at Oxford, Computer Science of Quantum Computing. I initially started this with Alex, then Alex moved away to Holland, then Alex got enough of Holland, Alex came back, I had enough of university, so I went away, and now Alex is teaching it again. That's kind of what happened. 5 years later, new book coming. I love it, like his name is misspelled, like Gogiosi. It means there's many Gogiosos. I mean, one is enough, believe me. Anyway, that's forthcoming in 2-3 months. It's going to come in 2 versions. This is going to be the cheap version. There's going to be a fancy, posh, expensive version too. Right. And there will be a whole series of video lectures. So people these days, they don't read anymore, they watch. So you can actually watch the entire book in video recordings. That's Stefano, by the way, giving a lecture. So we took a mix of people giving lectures. It's not just the 2 of us, it's a lot of different people. And so the entire book is now it's almost finished being videoed. Right. So I'm just going to briefly take you to a few of these chapters of that book. Right. So basically this is picturing quantum processes but without any heavy jargon and without anything like symbols. And it turns out it's much thinner. Like, I think it's like about 140, 150 pages with humongous font, So the story is still about like boxes and wires. So here you see a wire connecting a battery, which is a box, and a light bulb, which is the box. So the conceptual foundation of everything is still the same. You got boxes and wires. And wires is a place where particles travel, and boxes is a place where particles maybe are produced or consumed. That's the kind of idea. So the thing is, like in PQP, we kind of took an abstract perspective. We talked about systems and processes. But I think for teenagers, you really need to talk about particles. Anyway, maybe I was wrong, I don't know, but that's the decision we make. So we talk about particles. Right, so here are your wires and your boxes, all the same as before. You got input wires, output wires, and all that. And then you can plug boxes and wires together into something like this, which you can call a network or a diagram. So that's a typical story. And then the magic starts happening. The magic starts happening when you've got such an equation. Like, this is just a piece of rope, of course, and a piece of rope you can always yank. And then this is equal to that. So this equation is really where the magic starts happening, because you've got this little cup-shaped wire here. And what do you say then? You say, OK, let's treat this like a box. Let's treat this cup-shaped wire like a box. Let's treat this cap-shaped wire like a box. And then magic happens. This is quantum teleportation. Boom. Yeah, I mean, this was the first step. So this was the first big insight that sort of showed that this way of thinking about things actually can give you very, so teleportation, since the start of anonymous formalism, quantum teleportation took 60 years to be discovered. 60, by 6 people. So that's like, only one more 6 was, so I need to find another 6, so we at least have 3 6s there in the church. Okay, so here is the magic. You got this cup-shaped wire, which you have to think of as an entangled state, and now you can just slide boxes around. You can slide boxes around. And basically what's happening here is you're creating the transpose. If you take a box and you slide it over an entangled state, you obtain a transpose. So a lot of linear algebra starts to fall out of this system. And yeah, okay, here is then the teleportation picture. So this is a really badly drawn galaxy. This is a galaxy. So then the idea is like, you got somebody at one side of the galaxy, you got somebody else at the other side of the galaxy. So that person has a state which they want to get to this side. So you use this cap box, and you can see you can just slide the box to the other side. Of course, everybody knows that this is nonsense. This is nonsense because you can't, of course, signal. But okay, and then you have to go a step further, then you say, okay, we can't do this thing deterministically, and then you do a correction, and then you got quantum teleportation. So that's kind of how it works. So with this formalism, quantum teleportation is the first thing you discover, the first thing, not 60 years after. Right, and then the next big step was spiders. Duško and I, we had this paper. I remember I was in Palo Alto with Duško. 2 weeks completely wasted on fighting and nothing. And in the last minute before I ran to the plane, Duško said, "Monoid, commonoid." And okay, the result was spiders a few years later. Did you say monoid or commonoid? I don't know. What? Commonoid, okay.
You were complaining that it wasn't a monad, but it turned out.
Yeah, you were complaining. I said, oh, monads. I don't care about monads. And then Duško finally sort of bended and said, okay, no monads. Anyway, so this is a wire. This is a wire. So I'm going to explain what a wire is. A wire is a thing with 2 endpoints. Okay, you've got 2 endpoints. 2, not 3, not 1, 2. That's a wire. And what happens if you take 2 wires and you connect them together, you get a wire. Maybe longer, but let's think of these as elastic, so there is no concept of length because it's elastic. So when you glue 2 wires together, you get another wire. That's really what it means to be a wire. A good wire, because you got bad wires which break, but this is a good wire. Now, that's a spider. And what is a spider? We could have called it like a multi-wire or a generalized wire. We decided to call it spider. And yeah, it's got 8 eyes, so it has to be a spider. Okay, so what does a spider do? When you connect 2 spiders together, they give you another spider, just like the 2 wires gave you another wire. So it's just a generalization of the idea of a wire. You glue two things together and you get, again, one of the same. That's it. That's a spider. What else should I say? Yeah, the person who actually had the insight of this Dushka and I did to actually have this idea of spider was a person called Eric Paquet. So the team was me, Dushko, and Eric Paquet. It was like basically a nut house. It was a total nut house. Right. So things get really interesting when you got two colors of spiders. So here you got green spiders and red spiders. And when green spiders and red spiders meet each other, they don't fuse. What happens is their legs fall off. Like boom, 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 their arms fall off. Now, the only sort of annoying thing is you have to be able to count to two, because it has to be two wires. If they connect with one wire, they don't fall off. If it's two wires, they fall off. So you need to be able to count to two to understand this principle. So right, and so we gave this thing a name. We call this thing, in technical terms, complementarity. Complementarity, like the idea of position momentum or X and Z bases. That's really what this thing is trying to incarnate. The idea of like complementary observables. At the later stage, we came up, Ros is sitting there, with a notion of strong complementarity. Oh yeah, all this stuff that was, the color stuff, that was Ros there. Say hi, Ros. In 2007, 2008, in a bus in Iran. Okay, so the thing is you can actually start to do interesting stuff with these spiders. So what you see here is a quantum circuit. Okay, we're quantum now. Quantum circuit, think of this as C0 gate, this is the control, and then this is where you do either not or. So these are three C0 gates, and we want to know if this is the simplest way we can write this circuit, or can we simplify it? So okay, spiders fuse. So you see, all these spiders of the same colors fuse. The three green spiders in the middle fuse. The two red spiders on the left fuse. You see? That's spider fusion. Now you see that there is two wires between the red and the green spider. So what happens? They fall off. So, and then, I mean, you know, spider is a generalization of a wire. So we've got a spider with two ends. That's just a wire. That's just a wire. So we basically figured out using spiders that this circuit can be simplified to this circuit. And this may look really stupid, but at the moment, quantum computers aren't very big. They're quite small, they're very noisy, so you want to get your circuit as small as possible. And this stuff is now setting the state of the art on how you do that. This is the best you get. All the records are thanks to this stuff. I don't know, Alex Kissinger is not here, I think. So he's one of the pioneers there. Who else? Ross, you have paper on that too, right? Yeah, yeah. Is there anybody else here who does circuit optimization using ZX? Harney is not here. Wow. That's weird. Right. So I'm not going to say anything more. So this was basically the material of the two first chapters, but I'm not going to give away anything more because we are doing an experiment. We are doing an experiment in which we are teaching kids this stuff. And then, okay, you got these Oxford people here who actually take a normal quantum course. They take Jonathan Barrett's quantum course, and we're going to give them the same exam. Same exam. The kids get the stuff I was just showing you. These dudes, they get Jonathan Barrett's course. Same questions, of course, slightly differently formulated because they need a different language than that. Same exam, and we're going to see who wins. And the reason we can't publicize this book, it's not because of the kids, it's because of these. Because they could cheat and use the book instead of Jonathan Barrett's course. That would be cheating. So that's not allowed. So that's why we actually have to keep the book secret until that experiment is performed. But it's now being set up. Thomas, do we have a date? Is Thomas here? What is the timeline now? Yeah. Okay, I know the ethical approval is in and all that, so I saw Alex yesterday. Yeah, okay. Anyway, so that's something we're doing now. I mean, I've tried to do this. I mean, some people know that I've been talking about this for 5 years. It's simply impossible to do in academia. because people were actually obstructing us. They said, this is not science. This is not science. That's what they told me. This is not a thing you should be doing with your time. That's academia. And now the company, my company, Quantinuum, is paying for all of this, and for the book and for the videos. So that's the difference. Okay, so I made this slide. This is some sort of PR slide. These are now all the companies using these diagrams in some way or another. I mean, for a long time, people in mainstream quantum information just were making fun of us, that this thing will never lead to something useful. And it actually needed quantum industry because then it's, with quantum industry, it's whatever works is good. It's not whatever academics decide is good. It's whatever works is good. And this is the result over the past few years with like companies using these diagrams in some way or another. So that's a lot. And these are the ones I know about. These are the ones I know about. It's a growing list. Right. Everything. So when we start to do this, oh, there he is. He just walks in. Look, your face is here. So yeah, so we started to do this thing, like how much can we actually do with diagrams? And then the answer is everything. Because these three people, Amar couldn't be here, he's giving his invited talk somewhere in France, otherwise he would have been here. Kang Feng, I don't know what happened to him. And Harney, he just walked in sneakingly. They showed, and this was a process, this was just not one paper out of the blue, there was some sort of process, there was a team of Nancy involved. Miriam Bakkens had a very important role in that too. But they actually showed that any equation you can prove using linear algebra, like matrices and stuff like that, you can prove with these diagrams. So no difference. You can do as much with these diagrams as you can do with linear algebra, as far as equational reasoning goes. So that's the result from, what was it, 2018? Something like that, huh? I don't know. Oh yeah, 2018. So this was after, so can you believe? You spent 3 years writing a big book, 1,000 pages. And then the day the book is published, the most important result happens, and it's not in the book. That's very frustrating. Okay. Okay. I'm missing a little bit like, so combining traditional symbolic AI reasoning system and ML techniques fails. So a lot of people have been trying to combine machine learning with the typical like AI logic stuff, and there's people who are still doing this and working hard. But the reality is, nothing has really come out there that's sufficiently compelling. I mean, Steve tells me, yeah, no, but I'm not, is this going to work, Steve? No, it's not going to work, Steve says. Okay. So here is my view, like that propositional Aristotelian style logic is the inadequate description of the world. So we've been doing this thing for like more than 2,000 years, 2,300, 2,400, a world based on true and false, and very static. It's not the right description. I'm going back to the pre-Socratics, like Heraclitus. You remember Heraclitus, Parmenides. The world is just a place of constant movement versus the world is a statical place of properties. For some reason, people went for this. Probably because the other stuff people didn't know how to formalize. They needed category theory. So they had to wait for 2,000, 300, 400 years to actually realize Heraclitus' dream of a world in movement. And I think we should do this now too in AI. Okay, Aristotle is past his shelf date pretty much, so time to bin it. There is a fundamental incompatibility. I mean, computer scientists know this. And with their monad stuff, with this horrible monad stuff, they actually realized that there is a fundamental incompatibility between Boolean valueness and the distributional relational structures that we use to describe the world. Am I right, Disco? The monads don't commute. Where is Dan Marsden is not here. He's now Mr. Commuting Monad specialist. Okay, so and I think that diagrams give us a radically new compositional description of the world, and one which is perfectly compatible with machine learning techniques. As we have shown, starting in 2007, 2008, Steve and Marnouche is not here yet. So 2007, 2008, we used the diagrams to show that you can combine the sort of distributional vector space, vector embedding description people are now using in machine learning with the compositional structure of language. actually all these papers, if you read these papers, they're all wrong. Because we always say like, oh, we combine pre-groups and diagrams. You can't do that. Pre-groups don't live in this world, unfortunately. We never realized that, but there is no functor from pre-groups to vector spaces. It doesn't exist. You can't have spiders with pre-groups. A pre-group with spiders collapses into nothing. So we actually were always working with diagrams, although we set pre-groups. Anyway, now we don't not even doing pre-groups anymore. How am I doing with time? Probably I'm not going to get what I'm doing now, but it doesn't matter. Okay, so the new paradigm is compositionality. But you should be a little bit careful because there have been definitions. The definition of compositionality is typically attributed to Frege. Frege said compositionality means that you can obtain a description of the whole from a description of the parts and the way the parts are organized. Like, for example, in language, if you know the meaning of the words, you know how they grammatically are organized, you get a meaning of a sentence. But that stuff doesn't work quantumly. In quantum mechanics, you can't break down an entangled state to its parts and its structure. You can't. The only way to describe the entangled state is by describing the entangled state. So this sort of, the sort of bottom-up compositionality which has been dominating computer science is not really what we want. We need really, we need really like a true tensor, a tensor which is not Cartesian, which doesn't give you sort of the bottom-up build-up. That's really what we need. And we need to devise new logic of the world based on this new form of compositionality. That's what we need. I mean, we're doing it. Our team is called Compositional Intelligence. Richie, show your T-shirt. Caris, show your T-shirt. Caris. Show your T-shirt. This is Konstantinos' design. So we should give credit to the rest. There. That's now a trademarked logo, like that, right? Oh, you're not listening. I'm giving you a compliment that you made this trademark, this logo. Okay, back in 2005, I was in Montreal in McGill. 2004, yeah. And I was actually presenting this teleportation diagram. So there's me talking in Montreal, explaining teleportation in the category theory group in McGill, which used to be like probably the biggest category theory group in the world. I was a postdoc there in 2000. Duška was a postdoc there a little bit before me.
10 years later.
Huh?
10 years later.
10 years before that, yeah. Okay, so I was giving this talk, and I was talking about teleportation, and then there was Jim Lomnick was in the audience. I said, hey, Bob, this is grammar. I said, no, Jim, this is physics. No, Bob, this is grammar. No, Jim, old man, you don't know. You know, I thought he was getting crazy, you know. So that's Jim Lombeck. Right, 3 years later, this was in the computer science department at Oxford. So Steve was then faculty there. He was faculty before me. I was still like a physicist desperately looking for whatever job. No, actually I had a fellowship. I had an APRC fellowship. I had a 5-year fellowship and a promise from the department that I was going to get a faculty position. So Steve came there, new hire. And Steve started, and I met Steve in the printer room and introduced himself. Oh, I'm Steve. I said, hey, I'm Bob. Oh, yeah, you're Bob. Can you explain me what a tensor product is? That was the first thing he asked me. Can you explain me what a tensor product is? So Steve was busy with like vector representations of meaning. And then Mernush was there too. And Mernush had also worked with Lambek. Lambek came up with this new kind of grammar which was called pre-groups. And he had asked Mernush to do pre-groups for Persian. So she kind of knew I'm calling this like grammar mathematics. And then Steve knew meaning mathematics. And then Steve explained to us, I actually wrote a paper with Steve Pullman setting out the problem. Like, how do we combine meaning and grammar? Like, if you know the meaning of what I said earlier, if you know the meaning of words, you got vectors for words, and you know the grammatical structure, is there any way you can sort of devise or build meaning of a sentence? I mean, it didn't take long, you know. I just said, yeah, I know how to do that. Jim told me. Because these diagrams, they are exactly like they're exactly the same mathematics as grammatical structure. And of course, it's quantum mechanics, so they accommodate vector spaces too. I mean, quantum is about vector spaces, Hilbert space. So obviously, these diagrams can accommodate vector space and they can accommodate grammatical structure at the same time. So the solution was that, you know, I didn't even know what a pre-group was at the time. I just knew or how it, no, I knew what a pregroup was. I didn't know how it was used linguistically, but what I did know is that this was exactly the same categorical structure as my teleportation diagrams. It was exactly the same maths. That's what I knew. So that was enough for me to realize that's how we combine these things. Right, so okay, we wrote this paper, and now the name associated with this is Coecke. People call this Coecke. And just to take away the hype of having to publish your papers in fancy journals, this was the most horrible, we published this in the most horrible place. Like, there is actually pages double and stuff like that in the publication. It doesn't have like an ISBN or anything. Like, it's the most horrible publication ever. Doesn't matter. It's got like, what is it, like, because there's two versions of it, it's got like close to 1,000 citations, that thing now. Okay, so this is how it looks. So these boxes, they're meanings of words. Think of these boxes as meanings of words, just like before we had quantum states, now they're meanings of words. And these wires, they are literally the grammatical structure. If you work with pre-groups, and then you would use these grammatical gadgets, this particular kind of grammatical gadgets, what you use them for is somebody gives you a sentence and they allow you to verify whether the sentence is grammatically correct. And then, so the verification is a proof, and these wires here are a representation of the proof of grammatical correctness. So what we do is we take this proof of grammatical correctness and think of it as a linear map applied to the input vectors. So this gives you a vector, and then that's the vector supposedly representing the meaning of a sentence. There's lots of people, oh, there is she. Whenever I talk about something, they walk in. I don't know how this works. Yeah, okay, I'll show you, here is your face. Okay, so like I said, this is the meaning of words, and this is the grammatical structure. And then we got a lot of attention at the time, and we thought we were going to be superstars and stuff like that, but it didn't happen. It didn't happen. And the reason it didn't happen is because what this dude had said a while before, nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy. Fine. So the problem we had, not me, because I don't work with machines and computers, but like Steve and Marnouche and Dimitri and at Greffenstedt, they were trying to do these things on classical computers, and they got really good results. They outperformed other methods and all that, but it didn't scale. It didn't scale because, I mean, let's go back to Jim. Jim, okay, here we're back with Jim. So, okay, this is grammar, and this is Coecke, but it's quantum model, it's quantum teleportation, it's quantum model. So it really doesn't scale on a classical machine because it's exponentially big. So when Steve and Marnouche and Dimitri and Ed started to build the tensors needed, they exploded. Right, Steve? They exploded. They were too big. They were too big. And Steve is joking now that even at the time, I said, oh, Steve, you just have to wait for a quantum computer. And that was actually a joke. That was actually a joke. 2 minutes? Right, okay, 2 minutes. So what am I going to do with the rest of my time? So I mean, I'm not going to go, so the first paper we wrote was Will Zeng and I. So now I'm going to, and then all these people, Alexis is here, Giovanni, I don't know where Giovanni is, Konstantinos. We actually did this thing on quantum computers. This was really just before COVID lockdown, literally, like a week before COVID lockdown, we did our first hardware experiments, quantum natural language processing, and then we made it bigger. And gradually, all the people I used to work with before, they all started to come back and join us. So Dimitri came back, everybody just started. Robin is somewhere here. Okay, and now, then we gave all that stuff to the world. I mean, now you know where the name Lambeck comes from. Now you know it. That was the McGill person. That's where the name comes from. So we sort of shared and made this software available as an open source. So now everybody can do quantum natural language processing. I mean, we made a few covers in Forbes with that. Boom. I just want to show one. So I'm not going to go through this because this has been out there. We used the same stuff to make some music. What you see, that was with Eduardo Miranda. And we became #1 in the classical charts. Believe this. #1 in the classical charts. Boops. what is it? Bob Cigar Bus. Yeah. This was a music made with help of quantum computer. You see, Abdel cover behind us. Okay. Okay, so the last thing I want to show is just an animation. So this is the stuff Vincent Wine and myself and Jono have been working on for almost 2 years, and now pretty much everybody in the company is working on this. So you start with this paper, the mathematics of text structure. So everything we have been talking about grammatical structure is only about sentences. So all this categorical grammar was always just about sentences. And how can you extend that stuff to text? That's the question. How can you extend all that stuff to text? So there is this paper, the mathematics of text structure, which I wrote a few years ago. But this was very naive. I mean, the idea was basically to rewrite this circuit like this, and then you can basically compose different sentences together. That was the naive idea. And I didn't realize that something magical was happening when doing that. And so let me just go through, I'm going to skip this. So this is the recent paper. It's not out there. It's not out there. Distilling text in circuit. So we basically took this idea of the mathematics of text structure and said, let's do this properly for all of English. So for the full all grammatical things in English, and let's try to turn all of English into circuits. And this is how it looks. So we actually had to come, because we wanted a mathematical theorem. We wanted a mathematical theorem, and I'm going to explain what a theorem does later. So we actually have to kind of cook up our own grammar. So this is not pre-groups anymore. This is some sort of a Chomsky-style tree grammar. And then we had to add pronomial links and stuff like that. So we basically cooked this grammar to get to a theorem. And I'm going to tell the theorem later. So this is the grammar. And then you start, you start to do things. Like we're getting rid of the pronomial links by connecting some wires. So now we get rid of the fact that it's all written on one line. Look, this is very important. This is all here, the text is written on one line. Here, we give up the idea of text living on a line. Up, so we turn things in boxes, boom, that's a text circuit. So sober Alice, who sees drunk Bob clumsily dance, laughed at him, becomes this circuit. Now, here is the magic. Like, probably this is wrong even. Je t'aime vraiment is French. I really love you is English. You see, the three structures are different. Three structures are different because word ordering depends on language. It's part of the grammatical structure which is language dependent. If you go to the circuits, these language differences vanish. Those circuits are language agnostic. So, I mean, there is a person, Hamza Wassim, I don't think he's in the room here. Oh, there's Hamza. And he's done the same for Urdu. And so we haven't finished the proof yet, but we're sure it's true. So you can see that these two different languages, English and Urdu, which have completely different tree structures, in the circuits they become the same. So here is a structure which is penetrating into what is really fundamental about meaning structurally. And another thing is that if I write many short sentences, like everybody should do because it's much easier to read, and I'm not a snob who actually uses a lot, or you're a snob and you use very long, complicated sentences, which nobody can read, they become the same in the circuit. These stylistic differences vanish too. So we actually have unveiled what I would say the core structure of language meaning with these circuits. And here I stop. I stop, I just put it. I stop.